So there are two main types of exponential functions. The first one we're going to talk about is exponential growth. So growth just essentially means that it's going to be going up and to the right. So we're going to be increasing as we get bigger and bigger values of x. So the domain on this one is going to be any real number we want. So x is an element of the reals, and that's it. For this graph in particular, the range would be y values. Those are also real numbers. However, our y values are always greater than 0, never equal to, never below. The y-intercept, in this case, the parent function, it would just cross at y equals 1. At x equals 0, it would be y equals 1. It is always, always, always increasing. So you would say it's increasing from negative infinity to positive infinity. And it's decreasing never. It's always growing. So again, we always talk about increasing and decreasing in terms of left to right. Now the x-axis, as I kind of alluded to earlier, is a horizontal asymptote. In other words, the graph is getting really, really close to 0 as x is getting really, really close to negative infinity. Or if you want to put it in kind of our standard end behavior, it's going to be as x approaches negative infinity, f of x approaches 0. So on the left side, it's just going down to 0, getting closer and closer, but never quite getting there. If you want to add the right side, as x approaches positive infinity, f of x would be going up forever, so we're going to say it goes up to positive infinity. This last point, I meant to just leave it as the word continuous. Doesn't need to have a colon there, because yes, it is continuous. We could have just left it there. So that's growth. It's going up and up and up, further and further as we go to the right. Now there's also exponential decay. That's the opposite of growth. So if y equals a to the negative x, so in other words, we have a negative exponent. The domain is going to be the same. So looking at this graph, you can still plug in any x value you want. Oop, that was a bad curly bracket. Let's try that again. So x is still any reals you want. The range for the parent function is still the same thing. Y is an element of the reals, just as long as our y values are greater than or equal, not equal to, just greater than 0. Y-intercept also has that y-intercept of 1, no change there. It's increasing never. It's decreasing forever, from the left side all the way to the right side. Now again, it has an x-axis. The x-axis is a horizontal asymptote, so it's getting closer and closer to 0 as x is getting closer and closer to positive infinity. So again, if you want to put it in terms of end behavior, it'd be as x approaches negative infinity, f of x, well, the left side of the graph is pointing up, so we'd say it approaches positive infinity. And then on the right side, we'd say as x approaches positive infinity, f of x approaches, well, in this case, it's going to 0, getting closer and closer to 0. Another point here, continuous, yes, it is. Again, just could have left that word there. So we got growth, which is increasing as we go to the right, and then decay, which is decreasing as we go to the right. So after we've been working with exponential functions for a bit, one thing we can actually use is like solving exponential equations. So if you have an a value that's greater than 0, so the base of your exponential is greater than 0, and it's not equal to 1, a to the x equals a to the y if and only if x equals y. The exponents have to be equal to each other. So looking at number 1, it says x to the 5th equals 2 to the 5th. We're supposed to solve for x. Well, x to the 5th equals 2 to the 5th. That's just x equals 2. Don't overthink it. Now, the next one, x to the 3rd equals 27. You might be able to identify that already, but let's see if we can rewrite this. X to the 3rd equals 27 can be written as 3 to the 3rd. In other words, x equals 3. So we're trying to essentially find what base makes that statement true.